Right, so welcome to another session, and today we are going to discuss channel equalization. So in the last class, we discussed the motivation behind channel equalization, and in this class we'll be going through its mathematical framework. Right, so we saw in the last class what is intersymbol interference. So we saw how intersymbol interference is because of so you have intersymbol interference, which is because of multipath in the channel. And we saw that intersymbol interference results in uh, intersymbol interference results in the merging of a symbol of uh, so basically say we are transmitting two symbols A and B. So it might happen that copy of symbol B is detected as symbol A, right? So that is what is intersymbol interference. And so we are going to see how we can mitigate this or remove the intersymbol interference at the receiver. So there are broadly two ways of removing ISI. So ISI removal. So one is in the time domain, which we'll be seeing in this class, and then we have the frequency domain, which is the OFDM orthogonal frequency division multiplexing. So that is in the upcoming weeks. So in time domain, we'll see how in time domain we can mitigate the ISI. So far we were having the signal model, which was yk is hxk plus vk, right? Where h is my channel CSI, which we had to estimate. X is my pilot symbol, and v is my AWG and Gaussian. Y is my observation. But now we will have a modified uh, signal model, and now we are having, say, uh, so the signal model is kind of like, say you have a transmitter and we have a receiver, and there are two paths to reach the receiver. So we have two paths with CSI H0 and H1. Okay, so we have two CSI H0 and H1, and what is basically happening is that at an instant you are receiving XK with H0, and you are receiving a delayed version of the symbol, which is XK minus 1, right, at H1. So this is your previous input and your current input, and they are both getting added together. And so this is basically interference of the symbol at k minus 1 with the symbol at uh, time k, right? So the first assumption in this signal model is that we have only two channel types or two multipath, right? So this is my assumption. We can have even a greater number of uh, channel paths also, but for simplicity and for ease of understanding, we are currently assuming that we have two channel types. Right. So what is my aim? So my broad aim is to mitigate the effect of ISI, and we are going to use time diversity. Now, what is time diversity, right? So, so far we have this transmitter, we have a receiver, and we are having two paths, right? H0 and H1 from where the signal is coming. So what we are going to do is that at the receiver, now we are going to do some kind of post signal processing, right? So we are going to perform some signal processing at the receiver end so that we can so that we are able to recover the information which we want. So what do we want, right? So see, we at time k, because we are looking at time k, and we are at time k, I should have obtained xk, right? So we need xk, right? And xk minus 1, which had to come in the previous time instant, is now coming at the current time instant and thus interfering with the current symbol. So we don't want xk minus 1, right? So xk minus 1 is my interferer, right? And xk is required, right? So we are going to perform some signal processing so that we can obtain xk. So what we'll do is we'll employ or we will take 3 observations at 3 different time instances. So we will be taking so just remember that please mute yourself. Uh, yeah, thanks. So just remember that for a L tap channel, right? If my channel is having L taps, we will be having L+1 equalizer, right? So we'll be having a L+1 equalizer. So for instance, here my L is 2, that is we have 2 multipath channel. So my R will be 2 plus 1, which is 3, right? So I will be requiring at least 3 tap equalizer. So it is not hard and fast that we need L+1, but if we have 3, so the it is we can obtain a much better estimate with the larger number of taps which we have, right? So with better accuracy, we'll see that. But just remember that as my number of taps increases in the equalizer, so more the number of equalizer taps, larger is the complexity, right? So the post-processing complexity will keep on increasing. Yes, someone has a question, I guess. Yeah,
So
please go ahead.
your notepad is not visible.
Screen is not visible.
Yes, yes, sir.
Is it not visible to, and can anyone else confirm that? Mohit, can you
No, sir.
confirm?
This is visible for me, I think.
All right, Manish
I think
says it's visible.
ma'am. I think ma'am have some network issue.
Ma'am, can you join
I
again?
think so.
Can you log out and log in again?
Sir, not notepad is not visible.
Let me check with someone else. Aranya, are you? Can you listen to me? Mohit.
Yes, sir. Yeah.
Yeah, is my
It is visible.
pad is visible, right? In which I'm writing.
Yes, it is visible.
Okay, so I think Vijay Lakshmi ma'am, you can please log in again. Just log in
Okay, sir.
again. Yeah,
Okay.
yeah. Just log out and log in again. So fine. So what is my signal at time k plus 2, right? So at yk plus 2, we will be having h0 xk plus 2 plus h1 xk plus 1 plus vk plus 2, right? So if you see at yk plus 2 is being we needed xk plus 2 and it is being interfered by xk plus 1, right? Similarly, yk plus 1 is having xk plus 1, which is my required signal, and xk is my interferer. Similarly, at yk, I should have got only xk, but I am also getting xk minus 1, which is my interferer. Okay, so if we write it as a matrix form, so this is my y matrix, which is having the 3 y's, yk plus 2, yk plus 1, and yk. Ma'am, is the screen visible now?
Sir, no, this time is not also visible.
Okay, so don't worry, we are recording it anyways, so you can see in the recording, right?
Okay,
So
sir.
yeah, no issues. So we have the y vector and the H matrix, if you see. So at k plus 2, if we take each time as a column, so at k plus 2, we have h0, right? So see, h0 is with xk plus 2. So there is no other term having xk plus 2, right? So only h0 will be there, and yk plus 1 has no term having k plus 2 time index. Similarly, yk is also not having any k plus 2 time index, so they both get zeros. And similarly, you have h1, and this is kind of a cyclic shift, right, which is happening. So this is called our channel matrix, which is h, right, and this is being multiplied with our X. This is our pilot matrix, right? And pilot matrix is having k plus 2, k plus 1, k and k minus 1 terms. And similarly, we have the V matrix, right? So, okay, Vk minus 1 won't be there, right? So at the receiver, we need to process the output signal for 3-time instance, right? So we are kind of post processing the signal so that we can obtain xk. What do we need? We need xk. This is my required, right? This is what I require. So let us consider something which is called equalizer weights, which is represented as vector c, right? And since we considered 3 equalizer taps, so for yk plus 2, for yk plus 1, and for yk, so you can just assume, say you have a AC vector, right? So you are say taking yk, you are then taking yk plus 1, then you are taking some yk plus 2, and you are then say multiplying it with say c0, you are multiplying it with c1, you are multiplying it with c2, right? So it is kind of tapping, right? So if you see from that analogy, so this is my receiver end, and here we are post processing the outputs which we are receiving. So C transpose Y can be written as C vector, and this is our Y vector, right? So initially, what did we have? So we had initially Yk is Hxk plus Vk, right? And now we are having some C transpose Y, which can be expressed as C transpose Hx plus C transpose V, right? So I'm just multiplying C transpose in the LHS and RHS. So if we see this term C transpose Hx, right? So we have, this is my C, this is my C transpose. This is my H vector and this is my X vector, right? And what, just remember, what did we desire? We want xk, right? We know what xk. So to get xk, this C transpose H should come in this form, right? 0, 0, 1, 0, so that 0, 0, 1, 0. So this is what C transpose H, right? And if you multiply it with this X vector, xk plus 2, xk plus 1, xk minus 1, right? So what will you get? You will get xk, right? So this is my C transpose Hx. So this is this term. Just try to link what we are writing. So C transpose H times X, right? So we desire that C transpose H should be 0, 0, 1, 0. 1 will be in this position, right? If we want xk, right? If we want say xk plus 2, so if xk plus 2 is required, then our C transpose H will be 1, 0, 0, 0, right? Similarly, if we want x k plus 1, then 0, 1, 0, 0 is what we desire. All right. So this is how we are kind of zero forcing the weights. All right. So we are zero forcing the or we are forcing that the post processing weights should be 0. So that is why this strategy is also called zero forcing strategy. This is called a zero forcing strategy because we are forcing the post processing weights to be 0. Right. So we desire that C transpose H should be 0, 0, 1, 0 so that we can easily obtain xk. So now what to do? So let's take the transpose of it, right? So C transpose H transpose. So the RHS becomes, so it was a row vector. In this step, it was a row vector, and now it becomes a column vector, and we are representing it as one vector. All right. Okay. And what is C transpose H transpose? This is H transpose C, right? So we are again using the property A B transpose is B transpose A transpose. Okay. So now what we want to do? We want to minimize this error. What is my error? 1 minus H transpose C squared. All right, just try to understand. So what we are saying, we are, since we are zero forcing C transpose H to be 0010, right? So therefore it we need to force it to be 0, right? And to force it to be 0, we want to and what will be minimum of error? It has to be 0, right? So if uh, H transpose C becomes 0010, then they will subtract with each other and get 0, right? Which is the minimum possible error, because error can't be negative. So right. And how to solve this? So we had seen that if we have this kind of least square error where we have this y minus xh squared, then it results in the Moore-Penrose pseudo inverse, which was h hat is x transpose x inverse x transpose y. So if we use the same analogy where my y is basically vector 1, x is my h transpose and h is my c. And if we have fit this analogy in minimizing this, so we get c hat, which after solving comes out to be h transpose inverse h into one vector, right? Where my one vector is 0, 0, 1, 0, and this y1 is here again because we want to find out xk. Right? We want to find out xk. So instead of estimating h, we are going to estimate c through post signal processing strategy. All right, and just remember that in this strategy we are using yk plus 2, yk plus 1, yk, right? And so we are basically using that different time instants, right, at the same antenna, and this is called time diversity, right? This is called time diversity. That is, we are exploiting the different uh, time instants so that we can improve or compute better estimate, right? So this is called time diversity. So there are actually many diversities exist. For instance, this is time diversity. Similarly, we can have space diversity. So in space diversity, we have multiple antennas which capture the same information, right? And we try to post process them. Similarly, we have the frequency diversity, which you will see in OFDM. So we have, so we try to, use different kinds of strategy so that we can improve the estimate which we require. All right. So what is my x hat which we wanted? So it is C transpose yk. So this is straightforward now. So my main aim in equalization is to find out what is my C vector instead of H vector. So once we find out C vector, we'll just multiply C vector with Y vector and that's it. Right. And as I said earlier, that this technique is called zero forcing because we are forcing the other weights whose signal which is not required for us to be 0, right? So in this case, we wanted xk. That is why we had 1 in the third position. If we wanted xk plus 2, my c vector should be something like this, right? Similarly, if I want xk minus 1, it should have been something like this. So I'm zero forcing my vector so that I can obtain the required signal, right? Now, since this so again, now what is the approximation error? Now, why do we have approximation error, right? So if you remember in so far what we studied, that at the receiver we are basically tapping at the receiver. So say this is yk plus 2, this is yk plus 1, and this is yk, right? And so the larger the number of taps which we have at the receiver, the more better is actually the signal which we want to get, right? So if I have, say, a lot more values, if I have, right, say yk minus 1, and similarly yk plus 3 and so on. So the more the number of tabs we have, the better is our estimate. But then the problem is that the complexity increases. Right, the complexity increases because for each pilot matrix, my H matrix increases. Right, so this is a big problem because this is a time domain technique. So the time domain strategies are very uh, computation intensive. Right? Right. So far we have the C vector, right, which we derived earlier. And what is my approximation error? My approximation error is S transpose C minus 1, 2. So 1, 2 is sorry, 0, 0, 1, 0. All right. So why is it called 2? Because this position is 0, this is 1, this is 2, and this is 3. So this is purely by this is a subjective notation. So the current course instructor has this kind of notation, so I'm also following this notation. But if you see some other book, possibly there can be some other notations. Don't get confused. This is just for notation purposes, right? So now here, if you substitute the value of C, so which is H transpose inverse H 1, 2 vector. So and then if you solve it, so let us consider this entire matrix as PH, right? And now if you look to solve this equation, which we have, so there are a few properties which you should know, that PH transpose is PH, right? So what is PH? PH is H transpose inverse H, right? So this is your PH. So what the first claim what we are saying is that PH transpose is PH. The second claim is PH square is also PH, right? So if we use these two properties, then we'll basically now this is what this is a norm square, right? This is the square of norm. Okay, what is norm? So again, if you have a vector, say x is a, b, c, right? Then norm of x is under root a square plus b square plus c square, right? And norm of x squared is a square plus b square plus c square, right? So this is square of the norm. So because we are considering here matrices, so this can be split as this in step 1, right? And we use a property that PH transpose is basically PH and I transpose is I. That is transpose of a identity is identity itself in step 2. So in step 3, if you solve this completely, we basically get that the error, that is approximation error. It is the approximation error for equalization is given by this step, which further becomes this. So if you are not able to understand the this, because this is a very complex matrix notation, so don't worry, we'll be solving some problems very soon, and in that you will be able to understand the meaning of this matrix notation, right? So what is the meaning of PH22? So PH22 is basically if you have a PH matrix, which is your projection matrix, right? And say you have some A, B, C, D, if you have say some elements. So as per the notation in this course, the first row is 0, right? So this element is 0, 0. Similarly, this element is 1, 1. And say you have some Z here, which is 2, 2 element, right? So we have the 3, so at the so row 3, column 3 is my 2, 2 element as per the notation in this course. And so yeah, the counting starts from 0, 0, right? So yeah, any doubts up to here, any conceptual doubt? And I'll switch to some problem solving so that you can understand the formulas. Any doubt? No doubt. So OFDM will start in the next class. So so this is the week 6. So let us start. All right. So we are given a signal model. Yk is phi xk minus 2xk minus 1 plus vk. We have a 2-tap channel equalizer. All right. So it is now specified that we have a 2-tap channel equalizer based on yk and yk plus 1. Right. So first we have been asked what is the effective channel matrix H. Right. So what will be yk plus 1? Yk plus 1 will be 5 times xk plus 1 minus 2 times xk plus vk plus 1. Right. So you can also solve with me. So if you have any doubt at any instant, you can just ask me. And similarly, yk will be 5 times xk minus 2 times xk minus 1 plus vk. Right. So what we need the channel matrix basically. Right. So my H will be 5 minus 2 0 0 5 minus 2. So this column is basically at time index k plus 1. This is at time index k. This is at time index k minus 1. So my answer is B. So if anyone has any doubt, can just ask. No. Right. So again, this is the same question as the previous one, and we need to compute the zero forcing equalizer, and again we have 2 taps, yk and yk plus 1. So what was my formula for the equalizer? So it was H transpose inverse H times, and see, we want to detect xk, right? We want to detect xk. So my one vector will be my one will be at this second position, right? This is represented as 1 2, right? This is represented as 1 2. Okay. So we had obtained the H matrix here, right? So this is my H matrix. So let us do H transpose. So we have 5 minus 2 0 0 5 minus 2 with 5 0 minus 2 5 0 minus 2, and if we solve it, we'll get 29 minus 10 minus 10 29. Okay. Now we want the inverse of this matrix. So H transpose inverse. So this will be 1 by 29 square minus 100, 29, 10, 10, 29. Okay. Right. And now what we have to do? H transpose inverse. And again, we have to multiply this with an H, right? So yeah. So I have 1 by something, right? So let me just keep this denominator as it is. And we have this 29, 10, 10, 29, and we are going to multiply it with H. 5 minus 2, 0, 0, 5 minus 2. And this will come out to be 1 by something. This is 145. You can solve it at your end. So I have solved it beforehand so that you can save some time. I think this will come here. This will be 1 by something, and this is 145, 50, minus 8, 125, minus 58, minus 58. Okay. And now we want to, final step is H transpose inverse H into 1, 2. So what will happen is that so when we multiply this with, when my 1 is at the third position, I will be just, left with these elements. Okay, so it is 1 by something, and this is minus 8 and 125. And if you see, you have just look at here. So you have minus 8 and you have 125, right? So so the answer is x hat, and of course 29 square minus 100 should be 741. Okay. So anyone has any doubt in this question?
Here I2 would be 0, 1, 0 only, because only two they are taking, like yk and yk plus 1, not yk plus 3. R is 2 here only.
Right. Okay.
Yeah.
Yeah.
So it would be 0, 1, 0 only.
Yeah. Thank you for the observation. Yeah, but yeah, that does not change the result. Yeah.
Yes, the calculation would be correct because we have taken middle column only.
Yeah. Thank you for pointing it out. All right, we move ahead. So, all right. So this problem is still, as the previous one. And what has he asked? So let the equalizer be denoted as C, let the effective channel matrix be denoted by H, and the approximation error. All right, so approximation error. So I will use this straightforward. So this was derived in class, and this is this, right? So our approximation error is 1 minus H transpose H transpose inverse H, and this is 1 comma 1. So this is our answer, right? Okay, we move ahead. So now for the same question, the approximation error, we need to compute it. So right, let us compute it. So 1 minus H transpose H transpose inverse H, right? So we need to find out what is this. So in this question, we have computed already what is H transpose inverse H, right? So we already have this thing. So let me just write it. Yeah, so let me just, if we solve this, so this will be 1 by something. This is my, this is actually 1 by 29 square minus 100. So 5 0 minus 2 5 0 minus 2 and 45 minus 8 minus 58 50 minus 125 minus 58. So this was H transpose inverse H, which we computed 2 questions earlier. And if we solve this, this is 1 by 741, 725 minus 40 minus 100 minus 40, 641 minus 250 minus 100 minus 250, 116. So now we need the 1 comma 1 position of this matrix, right? And the counting starts from 0. So this is basically my 0 comma 0 element, and this is my 1 comma 1 element, right? So 641 is my 1 comma 1 element. So we will be doing 1 minus 641 over 741, and this is basically 100 over 741, which is my approximation error. So any doubt in this question? No doubts? Right. So the equalizer which we designed using the least square criterion, so it is a zero forcing equalizer, right? Because we are forcing the weights of the symbols which we don't need to be zero, right? So we are forcing them to zero, hence it is called zero forcing. Right, so now we have a different signal model. So we have -3 xk, xk minus 1 and vk. We have again a two tap equalizer with yk plus 1 and yk. All right, what is my h? So let's again do it. So yk plus 1 is -3x xk plus 1 plus xk plus vk plus 1. Yk is -3xk plus xk minus 1 plus vk. So my h is -3 1 0 0 -3 1. Right, so this is D. No doubts, right? Okay. Now the expression of the projection matrix H. Right. So the projection matrix PH, as it was done in the lectures. So this is H transpose, HH transpose inverse H, right? So which option is this? H transpose. This is option B, right? Okay. So now we need to compute this projection matrix. All right. So let us compute for this question. So we need to compute H transpose HH transpose inverse H. Okay, we need to compute this, and our H is -3 1 0 0 -3 1. Right. So first I'm doing HH transpose. So this will be -3 0 1 -3 0 1 -3 0 1 -3 0 1. And if you solve this, so you will be basically having this is 9 plus 1, and you have 0. This is -3 plus 1. No, plus 1 will be here. This will be -3, and this will be 9 plus 1. Right, so we have 10 -3 -3 10, and now if you take its inverse, so this the determinant is 1 by 10 square is 100 minus 9, and you have 10 3 3 10. So this is basically 1 by 100 minus 9 is 91, and you have 10 3 3 10. Okay, so now if we multiply H transpose with this stuff, so let's do that. So we have 1 by 91 comes outside, and you have -3 0 1 -3 0 1, and you have 10 3 3 10, and you have to multiply it with h again. So this is -3 0 1 -3 0 1. Right, so we need to solve this, and if you just solve this, this is a straightforward matrix operation. So you will be getting 1 by 91, 90 -3 -9 -3 82 minus 27 minus 9 minus 27 10. Right. So this is option D. Right. So you can just do it. It's a straightforward matrix multiplication. Any questions? Okay. So same question as above, and approximation error. All right. So what is approximation? 1 minus the projection matrix, and see we want to detect xk. So this is 1 comma 1 element. What is 1 comma 1 element in this projection matrix? So again, let me just write a projection matrix. So this is 1 by 91. 90 minus 3 minus 9 minus 3 82 minus 27 minus 9 minus 27 10. Right, so the 1 comma 1 element is 82, right? So this is 0 comma 0 element, and this will be 1 comma 1 element, right? So 1 minus 82 by 91, and this will be 91 minus 82 over 91. This is 9 by 91. Any doubts? No doubt. Okay. So the final question, we have the same signal model. R is still 2. R is still 2. And now we want to detect xk plus 1. Right? So far we were detecting xk. So since we were detecting xk, as I think Aranya pointed out that our matrix will be 0 1 0. But now since we want to detect xk plus 1, our this is my one matrix basically. So now it will be 1 0 0, right? And what will be approximation error? Basically, what they have asked. So in this case, our approximation error will be 1 minus ph, and now we will be considering 0 comma 0 position, right? So in the previous question we considered ph 1 comma 1 position, right? But since we want to iterate xk plus 1, so we are now considering the 0 comma 0 position. And what is the 0 comma 0 position? So if you again see this matrix, 0 comma 0 position is having 90, right? So 1 minus 90 by 91. So 1 minus 90 by 91. So this is 91 minus 90 by 91, which is 1 by 91. So it's 1 by 91. So any doubts in this? Any other doubt which you have regarding the assignment or this week's channel equalization? Feel free to discuss. Doesn't seem any.
Sir, please show the question number 5 again.
Question 5.
Question number 5.
All right. Just a minute. Yeah.
Okay, sir. Thank you.
Yeah, someone has raised hand. Aranya, go ahead.
Yes, sir. Actually, in last week, week 5, there was sigma square was given as 3 dB.
Right.
So, sir, actually, I knew it from minus 3 dB. Like in class, we have done it with minus many times. So for this, we should we use calculator in final exam because we don't remember generally the approximation 10 raised to the power like while converting.
Is calculator allowed? I think it should be allowed, right? Because this is engineering level. So I believe that normal scientific, I mean, the normal Casio calculator should be allowed. Yeah, which is a non-scientific one.
Sir,
Yeah, you can
sir,
use
I
that.
think calculator is not allowed because that I have in last time all digital things all not allowed in the exam.
Oh, is it? Okay.
When I was appeared in the last year exam.
Ma'am, so you can just put this in the forum, and possibly the course instructor will see into it. So
Okay.
yeah,
Yeah.
okay. You can just raise this point in the forum. Yeah.
Sure. I shall raise. Thank you.
Yeah. Yeah. Okay. So if nothing else, you can leave. Right?
Yes.
I don't have. Okay. Thank you.
Thank you.
Thank you. Thank you, sir.